So in this course, I'll introduce you to a few useful tools and concepts. For the QFT 1, 2, and 3 courses. So obviously, there's a wide variety of math that is useful in QFT. We've already seen some of it in Tibra's course. I'm just going to choose a selection of topics that are often unfamiliar to students that will be used in these courses. Most of it will be used in QFT2. And many of the topics we'll talk about have other applications. But the concepts and tools were chosen for applications to these courses specifically. So what we're going to discuss over the next 5 lectures are a few different topics, the first of which is distributions or generalized functions. And we'll spend approximately 2 lectures on this topic. And then we will discuss asymptotic series, again for approximately 2 lectures. And finally, summation, quotes of divergent series. So there are these topics. We'll be jumping around a bit when we move from topic to topic. There's some connections between these last 2 things, but the first part of the course will be somewhat disconnected from the second part of the course. So that's where we're going for the next week. And today and Monday, topic will be distributions. And let me just give you a brief some motivation for why we want to study this topic. So you all are familiar with at least one example of a distribution that's not an ordinary function. So distributions are a generalization of the notion of functions. So all of the functions you're familiar with are also distributions, or most of them at least. But one example that you're all familiar with of a distribution that's not a function is the point charge. So point charge has a charge distribution that is 0 for x not equal to 0. But it doesn't have a well-defined value at the origin. So this is not this last equation is okay for some applications of electromagnetism. All we really care about will be the integral of the charge density. We can integrate the charge density and get finite charge. But this is not a smooth function. It doesn't have a well-defined value at the origin. So the charge distribution for the point charge is proportional to the Dirac delta, which is sometimes called the Dirac delta function. It's a poor name. It's not a function. So that's one example that you're all familiar with. And in fact, that's the most important example of a distribution that's not a function. And understanding more carefully what the Dirac delta distribution is will have important applications in these courses later. We'll want to perform some operations on things like the Dirac delta that may not make sense if we try to think about it like something that's almost a function. And having a clearer picture of what exactly it is will make many of the manipulations and calculations we'll do in the QFT courses easier. So some things that you can do with distributions that don't make sense, if you think about ordinary functions, are to define things like the derivative of the absolute value function at x equals 0. So this doesn't make a lot of sense if we think about the absolute value function as a function, but this has a well-defined meaning if we think about it as a distribution. Similarly, we can have seemingly ambiguous integrals, something like the integral from minus infinity to infinity, 1 over x. So you might like to argue that by symmetry this is 0, but the integral from 0 to infinity and from minus infinity to 0 are both divergent. So does it really make sense for those to cancel off? But we can make sense of ambiguous integrals, seemingly ambiguous integrals, using distributions. And a little more input, we can make clear what to do with when we run across integrals like this. Distributions are also useful for computing functional derivatives. So functional derivatives, we take a functional derivative of some functional. In general, the result is not a function, but it's a distribution. In particular, if we're going to take multiple functional derivatives, it sometimes can be unclear what to do if you're thinking about it with infinitesimals, but there's a very well-defined procedure we can use using distributions that makes, in my opinion at least, it easier to compute functional derivatives. Another motivation for studying distributions are Green's functions. So a Green's function is a solution to an equation like this. We've got some differential operator acting on a Green's function. It's equal to the Dirac delta. So as you might expect, based on the appearance of the Dirac delta in this equation, Green's functions are not always functions. They're often distributions. And I'll say a bit more about these applications on Monday. And finally, many problems that we'd like to solve. Don't have any solutions that are functions, but they will have solutions that are distributions. So we can come up with a physically reasonable problem that just doesn't, there's no solution that exists that's a function. Okay. So that's y, we're going to learn about distributions. And just give you an outline of the next few lectures. So first, we'll go through some definitions. And so first, I'll expand a little bit on why it's problematic to think about, for instance, the Dirac delta as a function. So first, what they're not. And then discuss what distributions are. Then we will go through a few of the operations we can perform on or with distributions, namely derivation, multiplication, and composition. Some basic operations that we can perform on functions, and we like to also be able to perform them on distributions. And then we'll discuss a few applications, namely to functional derivatives, and very briefly about Green's functions. And so this is the outline for the next 2 lectures. I expect we'll probably either finish the definitions or just get started with the derivations today. And so approximately today. The rest be Monday. So I don't think I mentioned this, but notes have been posted on the wiki. So I'll update those periodically, but notes for the first couple of lectures are already there. Okay, so our most important example is the Dirac delta. This is a distribution that's not a function. And so we usually think of the Dirac delta as a limit of a sequence of functions that become more and more peaked at 0. And where the integral of each of these functions is 1. So a common way we can define it is just by, or you often see it defined is as a limit of sequence of top hat functions that are just piecewise constant. They get taller and narrower. So might say it. Find something like this. And so these functions all have the property that their integrals are 1 for all sigma. And they also have the property that f of x is 0 for x not equal to 0. So if we take the, so here f is the limit at any point once we take sigma small enough, eventually these functions will just be 0 identically. Okay, so this is the way you've probably seen delta, Dirac delta introduced. And it's not a function because delta of 0 doesn't make sense. And so ultimately, we will be able to define the delta as something like this, but it is dangerous to think about this as a function. And we'll see some examples of where things can go wrong if we try to think about delta as a function. So this, I put a question mark over this equation because we need to be careful about interpreting this. Okay, so it's not a function. One way we can see that is to define what we mean by a function space. And we can see rather easily that the Dirac delta is not an element of a rather general class, general or large function space. So a function space is a vector space whose elements are functions. Well, slight caveat that we'll come back to. With a norm that satisfies positivity, just the usual properties of a vector space of positivity. So the norm of any element of our vector space should be non-negative. Unique identity. There's only one vector with length 0. The 0 vector, or the 0 function. Triangle inequality. We add two elements of a vector space, take their norm, should be less than sum of the norms of the individual vectors or functions. And finally, linear homogeneity. Take the norm of lambda times f. We get absolute value of lambda times the norm of f. So basically what you'd expect, function space is just a vector space whose elements are functions. These are just the familiar properties that vector space should satisfy. And our main example will be the function space L2, which is the set of square integrable functions. And that means that if we integrate our function modulus squared from a to b to be finite. And a and b here indicate the which segments of the real line our functions are defined on. Okay. So the reason I put a blank space here, and that has to do with this second property here. So if we think about the elements of L2 of AB as functions, is there unique identity? A couple heads shaking. And why is that?
If you defined a function which was 0 everywhere except maybe 1 at a point, then its integral is still 0.
That's right.
So satisfy that.
Very, very good. So we could have clearly the 0 function as norm 0, but so does the function that's 0 almost everywhere for x not equal to 0, and example is 1 at a point. That also has norm 0. So we need to identify these functions if we're going to treat this as a vector space. So we just need to identify these functions and say that they live in the same equivalence class. And so two functions are in the same equivalence class if they just differ at a finite number of points. Okay, so this is a rather general function space. We haven't made any assumptions about differentiability or continuity, so some rather wild functions live in this space. But the space is not big enough to contain delta. And to see that,
sorry. Do we in general allow in the general function space functions of infinite norm?
no. This is the definition of this function.
But generally, so this is one example of a function space, or this is the function space we're defining?
Of the examples of function spaces I know of, I've never seen an example where you allowed infinite norm functions So,
Anyways.
Okay, I'm just saying, but if we're gonna follow this definition, then infinite norm is allowed, right?
just from these
Yeah.
properties.
Doesn't really matter, just asking.
I guess we just have to say what the norm maps to, right?
Yeah.
So if you say it's from the functions to the non-negative reals, then
Yeah,
it's
okay.
Yeah. For the examples we'll consider, we'll always want our function space to have finite norm. Yes.
L squared of a, b require that you choose any arbitrary values of a and b, or a and b fixed?
A and B are fixed. So this is a set of spaces. We could consider A and B to be minus infinity, infinity. Then we'd be considering functions on the real line, or we could get some subset. Okay. So delta is not in this function space. And to see that, we can compute the norm of these f sigmas. We try to define it like that. The norm of these f sigmas is easy to compute. Take the absolute value squared. It's just the integral minus sigma over 2 to sigma over 2, 1 over sigma squared, 1 over sigma. So the norm of this limiting function goes to infinity. So delta is not in this function space. Doesn't have a finite norm. Okay, so before we define distributions in general and figure out what delta is, just want to give a quick example of what can go wrong if we try to think about delta as function. So let's choose some e sigma so that the limit as sigma goes to 0, d sigma is 0 for x on 0, and the integral d sigma is 1 for all sigma greater than 0. So like the top hat function we looked at before, but the point is this argument is more general, and we consider any sequence of functions that satisfies these two properties. So we've got a sequence of these functions that has these two properties. It's becoming more and more peaked, and it has integral 1. So it's natural to think that it approaches the delta. But we have a sequence of functions like this. Then let's try to figure out the area of the limit. The limiting, or thinking of it as a function, even though it's not g. So we try to think about it, the limiting value of the sequence of functions. We can fit it inside this series of boxes, which have width epsilon for the bottom box, epsilon over 2 for the next one, epsilon over 4, epsilon over 8, so on. And so for each epsilon and each x, we can find sigma naught so that d sigma of x lies inside boxes for all sigma less than sigma naught. So top hat function is easy to find sigma naught. So if we choose epsilon and x, we can find a sigma naught so that g of sigma lies inside the boxes. If we just choose sigma naught to be less than epsilon, right. X, so we want x to be greater than sigma over 2. So we can just choose sigma to be, for our previous example, we can just choose, say, sigma to be equal to x. And far enough away so that function is just 0 for sufficiently small sigma. So we can fit the limit inside this series of boxes. And that tells us that the integral of this limit, if it exists, is less than a, where a is the area of the boxes. The area of the boxes is just epsilon plus epsilon over 2, it's epsilon over 4, which is just 2 epsilon. And this has to work for any epsilon. So that tells us that the integral of g of x dx is 0, which is not 1, which is, we switch the order of the limits. We do the integral first and then take the limit. We take the integral first and then take the limit as sigma goes to 0. We get 1, which is what we wanted. On the other hand, if we do the limit first, then take the integral, we get 0, which is quite bad. So here the order of the limit and the integral matters. So we don't want to think about the delta in this way as the pointwise limit of a sequence of functions. We can run into all kinds of trouble if we do that. For those of you who are familiar with the terms, the reason this works is, the reason we get this contradiction is because this sequence of functions converges pointwise to this, but not uniformly. So it's dangerous to think about delta as a function. A better way to think about it is as a distribution. And so one way to think about why we ran into this problem is that we were trying to think about delta as something that has some independent meaning when we take it outside of an integral. If we left everything, the delta, under the integral, as you often do if you're working with a point charge, you'll be looking at the integral of the charge distribution, and things work perfectly well there. But here, if we tried to take it outside of the integral, we're just talking about g of x, and we run into trouble. So what we can do to define delta is to expand on that idea, that it works, it behaves nicely as long as we keep it under an integral. And what is an integral? It's nothing more than a map from a function to the real numbers or complex numbers. And so that's going to be our starting point for defining distributions. So distributions are maps from functions to the real numbers. And we need to specify what functions we want distributions to work on. So a few intermediate definitions before we can define what a distribution is. So test functions are going to be the functions that distributions will map to the real numbers. And we will choose a set of test functions I'll call D. Will be a set of C infinity functions with compact support. Okay, so C infinity means that it's continuous with infinitely many derivatives. And compact support means it vanishes outside of some finite region. Okay, and so I'm making this choice for two reasons. One is this choice will simplify many of our derivations. These functions have lots of nice properties, but we could choose slightly less restrictive assumptions on our test functions, and most of the results will still work. Be slightly more difficult to do some of the derivations. The other reason I'm making this choice of test function space is that, in general, the more restrictions you place on your test functions, the nicer your test functions are, the wilder your distributions can be. So this is a very restrictive set of assumptions on our functions, which will allow us to have a rather large space of distribution. So can anyone give me an example of a function in this space? Can you repeat that? E to the negative x squared. Okay, so that's certainly continuous with infinitely many derivatives. It goes to 0 as x goes to plus or minus infinity, but it doesn't vanish identically. So we want it to vanish identically. Yes.
One of these top hat things, any one of them.
One of these top hat functions. So
One specific, not all of them.
So a top hat function, it has compact support, but derivative. Yes.
I don't have a precise formula, but we could take the top hat function and just smooth it at the places that are a problem by just taking exponential minus 1 over x squared.
Good, because that's a good idea. So you're imagining defining some piecewise function. So say f of x. You using this idea, building on that idea. So we want it to be 0, say for x greater than 1. And you're trying to smooth it. So that way, you're saying something like that?
Yeah.
Yeah. And we want it to match here. So if that will match if we put a minus 1 here.
Yeah,
So this is 0 at x equals 1, and all of its derivatives will be 0.
You could just smooth the plateau thing with sinh functions on each side.
Smooth this with sinh functions.
Plateau to a constant.
You want to multiply this by a sinh, or?
Just choose an interval for the transition in which this is a sinh instead of a...
Okay. We do want it to have compact support, so we do want it to be identically 0 outside of some finite region. Sinh.
Yeah, so like he's saying in the top part, you would say equals sine x in that region where it's not 0 everywhere else.
Okay. So sinh here. So your proposal is sinh x for x. For what region do you want to have to be sinh?
I want to substitute this part, the non-continuity, by a sinh.
Okay. We could probably do something like that. I'm not sure the exact formula you'd have. So the key point here is this. Although it's not analytic, the derivatives all match. They're all 0 at this point where we change it. So this is our choice of test function space. Again, we're choosing this restrictive set of functions so that we can have lots of distributions and also slightly simplify some derivations. Okay. So that's our test function space. And then sort of distributions are going to be functionals. The functional is a function that takes a function as an input. And so we can map these functions to the real lines, to real numbers. And so define a dual vector space, which are called D star, is a dual vector space. Of linear functionals of D to the real numbers. Not much would change if we mapped them to the complex numbers, but for simplicity, we'll consider maps to the real numbers. So that means that U is in D star if U of phi is a real number for any test function. Any test function phi in D. And linear means that we take u of a linear combination of test functions. We just get back alpha u of phi plus beta u of psi. And this is a vector space. So if we can also, it's also linear in, we can add together elements of this vector space as well. Okay. So we want to put one more restriction in order to get space of distributions, and so we'll call D prime is the space of distributions, and it's a continuous dual space. So that means that if we have a sequence, continuous means that if we have a sequence of test functions that approaches a limit, then u of phi n goes to u of phi. And this should be a uniform limit. So we take the difference between phi n and phi and take the norm, that will go to 0. That's what that means. So u is a distribution if u is finite, linear, and continuous. Okay, so delta is a distribution. It satisfies these properties. It's finite. So we have delta of x, phi of x, dx. That's phi of 0. So it's finite because test functions have a finite value at 0. So they have a compact support. They're continuous. So they have a well-defined value everywhere. So this is always a real number for our test function space. It's linear. So if we added together two test functions here, we get the sum of their values at 0. And it's continuous if sequence of functions approaches a limit, then those functions are getting close everywhere, and so their values at 0 are also getting close. Delta is a distribution in this sense. And this is probably the most common way you've seen delta written. This is an imprecise but sometimes useful way to write what delta is, because nowhere in our definition of delta do we need to define its value at any point. We can define delta just to be the another way we can write this is we can also define delta to be just the object that takes as an input a test function and outputs it's the value of that function at 0. So in this sense, delta is a functional. It takes an input, a function, outputs a real number. So this is perhaps the most natural way to write it if we're thinking about distributions as functionals. And most of the time I'll be using this notation. Sometimes you also see it written like this. So I like this notation. It shows that this is a functional. This notation you see in a lot of literature is not so good because these things are really different. This is not an inner product. It suggests that interpretation, but it's just some pairing. I don't like that notation, and I won't use it. Okay. So let's look at a few examples of functionals and try to see which of these match our definition. I'm going to write down a few examples. U of phi, integral of phi of x squared dx, v phi of 0 minus phi prime of phi plus 37 times the third derivative phi at e. W will be 1 if phi of 0 positive or 0 otherwise. And t can be the integral of phi of x or x squared dx. Okay, so I'm going to give you a few minutes to look at these examples and determine which of these are distributions. If they're not distribution, I'd like you to tell me why not. I'll give you a couple minutes to work, to think about that, and then I'll hold the class. We need some more time. Everyone done? You just nod your head if you are done. Okay. Okay. So I'd like you to take your hand and hold up a 1. Hold it in front of you if you think that it is a distribution. 2 if it isn't. Hold it there so I can see what you think. First one. 1 for yes, it is a distribution. 2, just hold it in front of you so I can see. Okay. Next one. Okay. Third one. The fourth one. Some disagreement on some of these. Okay, so I'm going to, you've all worked it out. I'm going to give you a couple more minutes, discuss it with somebody who had a different answer on at least one of these. And then I'll pull you again.
Yes, continuous.
What's this say? Wait, the one where above us, why wouldn't it be?
Yeah, it just went over next one.
That seems fine. That doesn't actually
But there's zero. But there's zero.
Maybe you can get one of these. I think this is what slowly goes to
It's not linear.
No, it doesn't. It's so general.
Oh, that
It's not
Say, like change.
if you want one. It's not.
As that.
I think it's only some data only have the ability for something to see.
I don't know.
These we don't.
First, the yeah, alpha and beta are just
linear.
This is fabulous. Change which is not linear. Test function. It's just a simple.
One.
oh yeah, sure. Sure, I have it.
Yeah.
Recal's function, the fridge function, and then check out my guy.
But only under.
What if the function
Or a subset of.
like if you take like goes down it's like a joke. That's not
Okay. Hopefully you've reached a consensus on some of these, if not all of them. I'm going to pull the class again. So again, 1, if it is a distribution, 2, if it's not, for the first one. Okay, more consensus. Can somebody tell me why?
It's not linear.
Not linear. Good. So u of phi plus psi is not equal to u of phi plus u. How about the second one? 1 for yes, 2 for no. More consensus again. Good, very good. Again, can anyone tell me why? It is or isn't?
I have a bad reason, but
Sure.
It's the Dirac delta, the derivative of Dirac delta, and the third derivative of Dirac delta, but we haven't defined it. So.
Okay. That's correct. But yes, so it's manifestly linear. It's finite. Their functions all compact support and are continuous. So that means function and all of its derivatives are bounded. It's continuous. So if you've got a sequence of functions that approaches phi, then all of its derivatives can also approach phi.
Now, I actually have a question.
Yes.
We consider function spaces to be spaces of equivalent classes of functions, and those equivalent classes are given by the by maybe being different at certain points. So how do we make sense of the evaluate the equivalence class at the point?
Okay, so that's a good question. So our first example of a function space was L2, which we put a very weak condition on the functions. So all we demanded that was that they had a finite integral. So in particular, functions there don't have to be continuous. They don't have to be differentiable. So we're allowed, there are functions in that function space that are the same everywhere except they differ at a point. That's something that's allowed based on the restriction we put on that function space. For our, it's under the board, but for our test function space, we put much stronger restrictions. We demanded that they're continuous and they have compact support. So if they're continuous, we're not allowed to, there isn't another function that just differs at a point, because then it wouldn't have a derivative there.
So does that mean that the Dirac delta isn't a distribution for that space? Because F1 and F2 are supposed to be in the same equivalence class, and yet the Dirac delta will give you a different value at each.
That's right.
Okay.
So that would be a poor choice of test function space if we're one. The Dirac delta to be a distribution. Okay. The third one. Good. Can somebody tell me why this is not a distribution?
It's in the dual space, but it's not continuous.
Right. Not continuous. Why isn't it continuous?
Because it changes abruptly with the value of the function at 0.
Right.
It goes from negative to positive.
Good. Not continuous. We could have a sequence of functions that approached by approached, so the value at 0 approached 0 from below, so it would abruptly change.
Can you also say that it's not linear because you might have two functions that are less than 0 at 0, but then when you add them, oh, I thought that said less than 6.
Oh,
Yeah, I guess they
so it's, yeah, sorry, it wouldn't change much if it was 6. But not linear too. Yes, I think you're. Yeah, not linear. Okay.
Think about this.
What's the fourth one?
I have a question. Do we suppose that the total domain of the compact supported function is R?
Yes.
It changes the answer.
Yes. I'm always going to consider that as their domain. Okay, going to see more agreement than before. Can somebody tell me why this is not distribution?
Not finite.
Not finite. Why is it not finite?
If you have finite value of phi at 0, then your integral will diverge.
Great. Good. Okay. Good. So I just want to elaborate on the statement I made before when I said that you know lots of examples of distributions, namely ordinary functions or most ordinary functions. In particular, functions that are locally integrable are distributions. And what I mean by locally integrable, I mean the integral from a to b of f is finite for any a and b of the real numbers. So I'll often, and most people often, slightly abuse terminology. We'll say these functions are distributions. More precise way to say it is that locally integrable functions induce distributions. And what that means is that if we want to act with a locally integrable function on a test function, it's just defined to be the integral of f times phi. And so in this sense, locally integrable functions define distributions, but it's very common. Just use the same symbol for the function. This is just an ordinary function, and the distribution it induces. Okay. So I'll just summarize a bit for today, and we can resume on Monday with various operations and applications of distributions. So what we've seen is that you can think of the delta, direct delta, as a map that maps functions, test functions, to their value at 0. So if we think about direct delta as a distribution in this way, so there's a functional, everything works very nicely. And note that we don't have to think about the value. If we think about things in this way, we never have to make reference to the value of the direct delta at any point. So this notation is somewhat misleading, although it can be useful at times. And what we'll see on Monday is that with these definitions, we can unambiguously make sense of some seemingly ill-defined function expressions. For instance, one thing we'll define is derivation. So we'll be able to define derivatives of the direct delta and derivatives of functions that aren't smooth, that have jumps. So all those things can be done rather easily and rather straightforwardly if we think about things in terms of distributions rather than functions. Doesn't make sense to define the derivative of a function that jumps or has some other discontinuity. That will all work out very well when we think of things in distributions. Are there any questions? Yes.
Is D star a subgroup of D prime?
Yes. So yeah, we can. So D prime, we're putting the additional restriction of continuity. So distributions are a dual space. They're not the most general dual space. We need that extra restriction. Yes.
You know the procedure of completion of a metric space?
Completion of the metric space?
Yes. Like we did to build the real numbers from the rational numbers.
Right.
I've heard, and I'm not completely sure exactly how, that you can do the same thing with functions to get distributions in which or something similar. You know
That might be possible. Let me think about that, and I can get back to you. Off the top of my head, I don't know the analogy there. Any other questions? If not, I'll see you this afternoon.